In this video on bonding, I will give an introduction to chemical bonding and then give examples of Van der Waals bonds and hydrogen bonds. In subsequent videos, I will cover metallic bonds and then ionic and covalent bonds. Before we begin, I'm going to assume you've seen my previous video with an introduction to chemistry and the periodic table of elements. Now that we have an introduction to atomic structure and the periodic table of elements, we can go on to discuss the core activity of chemistry, which is bonds and bonding. These bonds can be of 5 different types: ionic bonds, covalent bonds, metallic bonds, hydrogen bonds, and bonds formed by Van der Waals forces. Ionic bonds are the strongest bonds. Covalent bonds run the gamut from very strong to medium strong. Metallic bonds are very strong and very special with regards to metal tools and equipment we use in modern civilization. Hydrogen bonds are very common in nature's most important solvent, water. Van der Waals bonds are the weakest chemical bonds and the most easily broken. Though weak, Van der Waals forces are all around us. Ionic, covalent, and metallic bonds all involve the exchange or sharing of valence electrons. Hydrogen bonding is a result of a slightly positively charged hydrogen atom in a molecule being slightly attracted to a slightly negatively charged atom. That negatively charged ion may be part of another molecule, or the hydrogen attraction may be towards a negative region within the same molecule as the hydrogen atom. In Van der Waals bonds, no electron sharing or exchanges occur, although Van der Waals bonding does involve electromagnetic forces in the electron clouds that surround the atoms involved in the bond. The categories of bonds and phenomena that are a result of Van der Waals forces are very broad. In effect, a Van der Waals bond might be any chemical bond or attraction that does not involve the exchange or sharing of electrons. The Van der Waals forces are still a product of electromagnetic charges between atoms or molecules. Van der Waals forces are a result of atoms having a positively charged nucleus surrounded by a negatively charged electron cloud. Van der Waals forces can be repulsive as well as attractive. As an electron cloud around an atom is in constant motion, the attractive and repulsive Van der Waals forces are constantly fluctuating in strength. Van der Waals bonds are the weakest bonds with a typical bonding energy not exceeding 4 kilojoules per mole. Van der Waals forces are very short range, usually less than the distance of a few atomic diameters or less than 600 picometers. At less than 400 picometers, Van der Waals repulsion begins to exceed Van der Waals attraction. So Van der Waals bond strength is a sum of attractive and repulsive forces. The reason you cannot put your hand through a tabletop is the Van der Waals repulsion force between the electrons in your hand and the electrons in the tabletop. This Van der Waals repulsion is a direct result of the Pauli exclusion principle that prevents electrons or any fermion from occupying the exact same space at the same time. Van der Waals bonds might include the adhesion or wetting of a dry surface by a liquid, or the ability of geckos and other small creatures like spiders and ants to crawl straight up walls or walk across a ceiling upside down. The internal cohesion of a liquid or a solid might be due to Van der Waals forces. The surface tension of water is a Van der Waals force. The internal cohesion of water is a Van der Waals force enhanced by hydrogen bonding. Hydrogen bonding is just a special case of Van der Waals bonding. Hydrogen bonding is the bonding of a hydrogen atom of a hydrogen-containing molecule with a negatively biased atom of another molecule to form an intermolecular bond. The hydrogen-containing molecule might also bond with a negatively biased atom within the same molecule as the hydrogen atom to form an intramolecular hydrogen bond. The strength of hydrogen bonds depends on the atoms involved, and it varies from 1 kilojoule per mole to 160 kilojoules per mole. The strongest hydrogen bond energy of 160 kilojoules per mole are for hydrogen bonds involving the hydrogen bifluoride ion. Water-to-water hydrogen bonds have bond energies of around 18 kilojoules per mole. Water molecules, H2O, are the most common examples of intermolecular hydrogen bonding. The water molecule is a polar covalent bond. Each of the hydrogen atoms shares its one electron with the oxygen atom. Because the oxygen atom has a higher electronegativity than the hydrogen atoms, the two electrons from the two hydrogen atoms are drawn closer to or spend more time with the oxygen atom. This causes the oxygen atom to be biased negative. Likewise, each hydrogen atom, in losing part of its electron, becomes biased positive. So, if another water molecule passes by, its positively charged hydrogen atoms may attach themselves to the more negatively charged oxygen atom, thus forming a hydrogen bond. In water, whole chains of linked water molecules may form. This hydrogen bonding behavior greatly affects water's boiling point and how it freezes. The hydrogen bonding increases the water's boiling point temperature. It takes high temperatures and a lot of energy to break the hydrogen bonds and release individual water molecules as steam. Six-sided snowflakes are the result of hydrogen bonding. The hydrogen bond angles of water are such that as the liquid water cools towards its freezing point, the hydrogen bond chains wrap back upon themselves. The first water molecule of the hydrogen bonded chain bonds to the sixth molecule, forming a hexagon that becomes the basis for further crystal growth. The result is an ice crystal that has 6 branches. Six-sided snowflakes then form in clouds. In bodies of water, the six-sided ice crystal has a hollow space in the center that renders it less dense than the surrounding liquid water. So, ice floats on top of liquid water. Life on Earth would be impossible without hydrogen bonding and how it affects how water freezes. The fact that solid ice floats on liquid water is another one of God's blessings that make life on Earth possible. It does not have to be that way. Most solid-state materials are denser than their liquid state, so the density of water ice is an anomaly. If ice was denser than liquid water, then ice crystals forming in ponds, lakes, and the ocean during the winter months would sink to the bottom. Ice laying on the bottom of a body of water would be protected from the warm air and summer sunshine. Our lakes and ponds would never melt except for the top few inches on a hot summer day. Lakes would stay frozen all summer. Even the ocean would freeze solid. The Earth would be covered in ice from pole to pole, both winter and summer. Life could not exist on such a frozen world. Some scientists hold out hope that there may be life on the moons of Jupiter, Europa, Ganymede, and Callisto, because they believe there is liquid water oceans underneath their icy crusts. Life on the moons of Jupiter is pure speculation, but liquid water oceans under the ice of the Jovian moons is likely true. Is it a coincidence that water, the material most essential to life, also has the unusual property of being less dense in its solid state? It does not have to be so. I, for one, dismiss coincidence and credit the miracle of floating ice to God. There are many scientists who would agree with me regarding the miracle of floating ice, if only in secret. Hydrogen bonding also affects the boiling temperature of water. H2O has a molecular mass of only 18 grams per mole. One would expect such a lightweight molecule to have a very low boiling point. Carbon dioxide, CO2, has a molecular mass of 44 grams per mole. Carbon dioxide has no liquid state at atmospheric pressure and goes straight from a solid dry ice to a gaseous state at negative 109 degrees Fahrenheit or negative 78 degrees Celsius. Carbon dioxide has no hydrogen bonding. Water does not boil until it reaches a temperature of 212 degrees Fahrenheit or 100 degrees Celsius. Water's hydrogen bonds hold the water molecules locked together in their liquid state until enough energy is added to break the hydrogen bonds and allow the water molecules to leave the liquid in their vapor state. The water vapor forms steam bubbles that rise up through the liquid and escape in the common phenomenon that we call boiling. To say that the water molecules are locked together gives the false impression that the bonds are static. All nature is in motion. Bonds are forming, breaking, and reforming at frequencies of thousands of times per second. It is just that when energy is added, it interrupts the bond reforming process long enough for the vibrating atoms to move far enough away from each other that the bond does not reform, and we say the bond is broken. The Temperature range between the freezing and boiling point of water, 0 to 100 degrees Celsius at atmospheric pressure, is the temperature range at which all known organisms live. Life could not exist if water was not liquid over such a wide range of temperatures. No life we know of can survive boiling temperatures for more than a few seconds. Some hyperthermophilic bacteria can survive at high temperatures in deep ocean volcanic vents where the water temperatures exceed 130 degrees Celsius. These bacteria survive because the pressure is so high that the water is not boiling and there is no boiling steam bubbles that would disrupt their cell walls and kill them. Some organisms can survive freezing for months or even millions of years, but must be thawed above the freezing point of water for metabolism and other life processes to resume. And all of these remarkable properties of water are the result of the water molecule's polarity and its ability to form hydrogen bonds. Please watch my next video on the wonders of metallic bonds, followed by videos on ionic and covalent bonds.